SwayamPrabha. Digital India. Educated India.
I welcome you all to this session, and today we shall discuss about the regenerative steam power cycles. So, if we try to recall, in the last class we have discussed about the ideal regenerative cycle, and we have seen that the efficiency of the ideal regenerative cycle is equal to that of the Carnot cycle. So, you know that before going to discuss the regenerative power cycles, let us briefly review whatever we have discussed in the last class. So, if we try to discuss about the ideal regenerative cycle, what we have seen that so, this is what we have discussed in the last class, and we have critically discussed that though the efficiency can be increased using this special arrangement, that means if we can circulate this feed water through a coil which is placed inside the turbine, and the flow of water or feed water is in the direction which is opposite to the steam flow direction in the turbine, and so this is water flow direction and this is steam flow direction. So, this is steam flow and this is water flow, right. Idea was to increase the temperature of feed water before it enters into the boiler, and if we can do so, then average temperature at which heat is added to the cycle can be increased, which in turn increases the efficiency of the cycle. But at the same time we have also discussed that this arrangement, I mean though it is theoretically we can see that the efficiency can be increased and efficiency will be as good as the Carnot efficiency, but making such an arrangement in real applications is not an easy task, rather it involves both the operating cost as well as the initial cost. So, accounting for these difficulties essentially from the perspective of the operation of the cycle, in fact the plant, there are several other methods by which this regenerative principle can be used to increase the efficiency of the cycle. What are those? Those are basically is known as two different times, but you know that at least from the schematic, let us now briefly discuss about several other avenues which we can explore. See, this feed water which would be pumped back to the boiler should be, you know, I mean temperature of feed water should be increased. So, instead of allowing or instead of circulating this feed water through this coil which is placed inside the turbine, why can't we look for several other avenues, like you know that steam which is passing through the turbine is having high temperature, high enthalpy. At the cost of this expansion inside the turbine, we will be getting work output, but temperature of steam will reduce. So, if we can allow steam to expand isentropically, and if we try to bleed or extract steam at different points from turbine, and if we allow that steam to be mixed with feed water, I mean if it is not possible for direct mixing, why can't we design a device wherein this extracted steam will be allowed to flow over the stream of feed water, and essentially by virtue of heat exchange temperature of feed water can be increased. So, idea is, since this is not a practically viable method, we can look for other what I can say ways by which the efficiency can be increased for I mean by using the regenerative principle. One is, I mean the extraction or bleeding steam from the turbine, and that steam stream can be used to supply heat, I mean from the steam stream that temperature can be used to supply to the feed water, and I mean what we have studied in heat exchanger. So, idea is to extract steam, and that steam should be allowed to mixed with the feed water in one case if it is possible. We shall discuss that. If we allow the extracted steam to be mixed with the feed water, then the temperature of feed water can be increased. Such an arrangement is known as open type feed water heater. So, open type feed water heater. In short, this is OFW. So, in this case, why open? Because extracted steam will be allowed to be directly mixed with the feed water which is taken from the pump before it goes into the boiler. So, these two streams will be allowed to mix so that temperature of the feed water can be increased. But we shall discuss today that if this particular arrangement, that means if direct mixing of these two streams creates problem, I mean definitely from the operational point of view, we also can look for other arrangement like heat exchanger, cross flow type heat exchanger. So, the extracted or blade stream should be allowed to pass through a device, and feed water should be allowed to pass through the feed water tube, and if we allow steam to pass over the feed water tube, by the virtue of heat exchange phenomenon, we can increase the temperature of the feed water. Such an arrangement where these two streams are not allowed to mix directly is known as closed type feed water heater. So, this is closed type feed water heater. C F W. Now, we shall discuss these two different types of regenerative process in today's class, and first we shall take up this. So, in the next slide we shall discuss about the open type feed water heater. Let us briefly discuss this using the schematic diagram, and then we shall discuss, rather we shall analyze the effect through the TS by representing the processes in TS plane. So, you know that if we discuss this issue, so let us draw it. So, here so this is boiler. You know these 4 major components should be there. So, this is turbine, then second law of thermodynamics that you have studied puts a restriction that there must be a heat sink essentially to run this device in a cyclic manner. So, this is one pump, and we can have this is a device in which extracted steam will be allowed to mix with the feed water which is coming from this pump. So, if we give name, so this is 1, this is 2. So, you know that this is the schematic depiction exactly what we have discussed in the context of previous slide. Steam should be extracted from the turbine. This is not the steam which is taken exactly at the inlet of this turbine, rather steam is allowed to expand isentropically, and then at an intermediate pressure some amount of steam should be extracted. What would be that fraction of steam that will be extracted, that we will discuss today, but so basically after doing certain amount of work or after doing some work, steam should be extracted at an intermediate pressure, and that steam should be allowed to mix with the feed water which is pumped from the condenser into this device. So, this is basically open type feed water heater. Okay. So, now you have started in fluid mechanics, you know that the 2 streams are coming, and one stream is coming, this is basically steam which is having high temperature and pressure is also high. So, if we need to have efficient mixing of these 2 streams, we cannot directly take the condensate into this device, because the feed water which should be taken to this particular device shall have pressure which is equal to the pressure at which steam is extracted, otherwise mixing will not be efficient. So, to ensure that the mixing will be efficient, pressure of the feed water should be equal to that of the pressure at which steam is extracted, and that is why this pump is coming into the picture. So, this is pump 1. So, this is Q out and this is W in. If we do not use this pump and if we directly take the condensate, the collected condensate, if we take to this open type feed water heater, mixing will not be efficient, and if mixing is not efficient, heat exchange will not be efficient. Main idea is to have higher efficient heat transfer between these 2 streams, and that is why we need to make I mean we need to ensure that these two stream should be mixed at a given pressure, and that pressure is equal to the pressure at which steam is extracted, because this is the high pressure. So, after mixing that feed water temperature will increase. So, the feed water is now going to be mixed with the extracted steam, and since the to build up that pressure of feed water, this pump is used, and after mixing again the feed water, I mean we really do not know whether it would be water or it would be a mixture. So, whatever may be the case, we will discuss soon, that mixture will be again pumped back to the boiler. So, boiler is operating at a pressure, and that pressure is not definitely the pressure at which this mixture is having. So, we need to have another pump essentially to develop the pressure of the mixture equal to the, which is equal to the boiler pressure. So, this is another pump P2, so this is W1 in, W2 in. So, this is say 3, this is 4, this is 5, this is 6, this is 7. Okay. So, this is the complete schematic depiction of the regenerative power cycle having open type feed water heater. Okay. So, I hope you have understood why these two pumps are required for the smooth as well as efficient operation of the plant using this arrangement. So, this pump is required to build pressure of the mixture which is coming from the open type feed water heater, and that would be, I mean the pressure should be raised to the boiler pressure, and that is why the second pump is coming, and the first pump is essential to build pressure of the feed water for ensuring, I mean to ensure the efficient mixing between the between these two streams. Okay. So, this is the description. Here I was telling that that the steam you are extracting from the turbine and feed water is coming from this condenser, I mean condensate is coming from condenser. So, basically at 1 we know from our previous discussion that the thermodynamic state at point 1 is the saturated liquid. So, because pump cannot handle two phase mixture. So, so long as the pump is there to pump the condensate from 1 to feed water, then definitely the thermodynamic state at point 1 should be the saturated liquid. Okay. So, this is the saturated liquid, pressure is raised, and that is why this pump is there, and that pressure is the intermediate pressure at which steam is extracted. Now, what would be the thermodynamic state of the mixture after mixing? Would it be two phase mixture? No, because pump cannot handle two phase mixture again. So, the mixture which we shall get from the open type feed water heater is, I mean should be pumped back to the boiler, because the pressure of this mixture is less than the boiler pressure. So, we need to develop pressure, that is why the second pump is there, and if we need to pump it back, if we need to pump this mixture back to the boiler to complete the cycle, then definitely the thermodynamic state at point 3 should be again saturated liquid. So, the fraction of steam that should be extracted from the turbine at any point. So, this is the turbine. While steam is expanding isentropically inside the turbine, at any point from the turbine we shall extract steam. Fraction of steam that should be extracted will depend based on the criteria, that is the quality of mixture at the exit of open type feed water heater should be the saturated liquid. So, this is M1. So, if it is M1, if we consider per 1 kg of steam is flowing, then remaining 1 minus m1 kg of steam will be allowed to flow isentropically. So, if we consider 1 kg of steam is flowing and it is entering into the turbine, and if we extract m1 kg of steam and that m1 we need to calculate what should be that fraction. The condition is quality of the thermodynamic state of the mixture at state point 3 should be the saturated liquid. So, and remaining 1 minus m1 kg of steam will expand isentropically as usual up to the condenser pressure and the cycle will be completed. So, let us quickly draw the TS diagram. So, if we draw the TS diagram, okay. So, you know that say this is the boiler pressure. So, this is the boiler pressure, right. Now, you know that this is regenerative power cycle. So, this is modified Rankine cycle. So, steam is superheated beyond 0.3. What is done? Say this is the 3, this is the 5.5, right. So, when we shall draw the TS diagram, we shall look at the schematic depiction. You should not memorize, otherwise you will be doing mistake while drawing the TS diagram. So, this is the state point 5. So, you know that when steam is expanding inside the turbine, some amount of steam is extracted from the turbine rather at any point, and it is allowed to expand isentropically at an intermediate pressure. So, if we consider that another intermediate pressure is something like this, so this is P intermediate, and steam is expanding isentropically up to this point. So, this is 0.6. So, try to understand, it is not necessary that whether 0.6 should be on the superheated regime or it should lie on the saturated vapor line, that depends on the requirement. So, there is no any I think what I would like to emphasize over here is that the 0.6 whether it should lie on the saturated vapor line or it should be in the superheated regime, it is we have to design, because our entire objective is to increase the temperature of the feed water heater. So, higher the temperature of steam which is extracted from the turbine, higher will be the temperature of feed water heater. At the same time, you also need to ensure that if we take steam, maybe depending on the position at which steam is extracted, if we allow steam to expand, and the pressure, that intermediate pressure is very important. If we extract steam from a point, and if the temperature if the state point 6 on the saturated vapor line, we will be getting some kind of heat from the extracted steam, and that heat should be supplied to the feed water heater. If we do like this, that the point 6 is again in the superheated regime, and if we take that steam and if we allow feed water to mix with that steam, we shall be we will be getting another heat transfer between these two streams. So, that is based on the requirement. Okay. So, this is M1, and that steam is taken to the open type feed water heater, wherein the collected condensate is pumped, and these two streams will mix together. To ensure efficient mixing, we are having this extra pump, and finally quality or thermodynamic state at point 3 should be the saturated liquid. So, this should be point 3. So, try to understand this point is 3 because right. So, if this is the point 3 and then 3 to 4 the boiler pressure. So, this 3 to 4, so this is 4.4. So, let me erase it. So, this is 3, this is 3, right. And so, if this is the case, this is M1 kg, right. Now, remaining steam will as usual expand inside the turbine isentropically up to the condenser pressure. So, if we try to draw the condenser pressure over here again, so this is the P condenser and so this is 0.7 and state at point 1 is saturated liquid. So, this is 0.1 and it will be again pumped back to the, this is 0.2. So, this is 0.2. See 1 to 2. So, basically this feed water collected condensate should be pumped to raise the pressure up to that intermediate pressure, that is P6. So, P2 equal to P6, right. So, this is 0.6. So, I am writing P2 equal to P6, P1 equal to P7 and P3 equal, P2 equal to P6 equal to P3 and P4 equal to P5, right. So, what you can see, so this is 1 minus M1 kg. So, what you can see, try to understand, had this arrangement not been there in the circuit, we would have we would have obtained the feed water temperature at the at the inlet of the boiler is, say this is, if I use other color. So, this is the, so this is 3 prime and this is, this point is 3. So, this is the 3, this is the point 3. So, had this arrangement not been there in the circuit, we would have obtained the temperature of the feed water at the inlet of the boiler is 3 prime. If the boiler is operating at this, if the operating pressure of the boiler is remaining same. So, I would like to compare, I would like to tell you, if the operating pressure of boiler is same, that is P4 equal to P5, making use of this arrangement, the temperature of feed water at the inlet to the boiler is now T4. But what I was telling, had this arrangement not been there in the circuit, we would have obtained the temperature of feed water at the inlet to the boiler is 3 prime. So, T3 prime when OFW is not there, but T4 using OFW, right. So, using this arrangement we could increase the temperature of feed water before it enters into the boiler, right. So, having, when you would like to compare, we should have a common basis of the comparison. So, if the boiler and condenser, these two are operating at a given pressure, say this is P5 and this is P7. In that case, it is because of this arrangement we could increase the temperature of feed water up to this point, that is T4, but if this arrangement, I mean in absence of this arrangement, we could get the temperature of feed water at the inlet to the boiler is T3 prime. So, definitely this T3 prime is less than T4, right. So, it is because of this increase in temperature, by making use of this arrangement, efficiency of the regenerative power cycle can be increased. So, that is what is the objective of having such an arrangement. So, you know that I mean see, try to understand that we are increasing the temperature up to this up to this T4, but this increase in temperature is not associated with the additional fuel cost. So, this is not due to the additional supply of heat that is given to the boiler. Instead, this is coming from the by taking some amount of heat from the flowing steam inside the turbine. So, we should be careful that since we are extracting certain amount of steam from the turbine, the fraction of steam is very useful, because this fraction should not be substantial amount of the total steam flow rate, otherwise what will happen that W out would be compromised. So, we should be careful while extracting steam from the turbine. So, if we now look at what should be the fraction of M1, condition is fraction of M1 should be selected in such a way that the state at point 3 should be the saturated liquid. So, to obtain this M1, we need to apply steady state steady flow equation to the mixing process inside the open type feed water heater. So, just by doing this, let us briefly do this. So, if we apply, so fraction of M is very important. Only criteria is that state of the mixture at point 3, that is at the exit of the open type feed water heater should be saturated liquid. Okay. So, this is the point that we should keep in mind while calculating F1. So, now if we apply steady state steady flow to the equation to the mixing process, in open type feed water heater. So, this is steady state steady flow process equation. So, applying steady state steady flow equation to the mixing process in OFW, what we can write? We can write this is M1. So, you can write that what are the two different streams. So, basically if I use different I mean M1 into H6 plus, so M1 kg of steam taken from the turbine into the open type feed water heater is having enthalpy H6 plus 1 minus M1 kg of feed water which is taken from the condensate which is having enthalpy 2, right. So, this is very important. 1 minus M1 into H2 equal to how much? So, this is equal to H3, because eventually M1 plus 1 minus M1, that is 1 kg. So, 1 kg of working substance we will be getting at state point 3. So, this is H3. So, you can understand what would be M1. M1 will be equal to H3 minus H2 divided by H6 minus H2. H3 minus H2 minus H6 minus H2. So, if we can calculate enthalpy at the different state points, then we can calculate what should be the fraction of steam to be extracted from the turbine. Okay. So, fine. Now, to complete, you can understand what is QH. So, heat addition, just I am writing heat addition. So, this is Q in. So, what is Q in? Equal to H5 minus H4. And what is Q out? What is Q out? So, Q out is that 1 minus M1 into H7 minus H1, right, 1 minus M1 into H7 minus H1. So, 1 minus M1 into H7 minus H1. Why I am writing? Because these expressions will be required while solving numerical problems. So, this is Q in and this is Q out. If you know Q in and Q out, you can directly calculate what should be the thermal efficiency of the regenerative power cycle. Nevertheless, we also need to know what is the work input and what is the work output. What would be the work output? So, this is very important, work output, that is W out. So, this is W out. If since I am writing per kg, it is better to write in the specific form. So, Q out, W out is equal to M1 kg of steam is expanding from in between. So, some amount of steam is expanding and then M1 kg is extracted. So, what would be the W out? W out is, so as if we supply 1 kg of steam at the in the turbine, I mean if we supply 1 kg of steam to the turbine, then 1 kg will expand from H5 to H6, remaining 1 minus M1 kg will expand from H6 to H7. So, that is what is very important. We can write that is H5 minus H6 into 1 plus 1 minus M1 into H6 minus H7, right. So, that is W out and remaining is what is W in. So, that is pump work. So, you can understand. So, this is 1 minus M1. So, this 1 minus M1 kg is pumped by this pump. So, 1 minus M1 into H2 minus H1 plus H3 minus H4, that is the total pump that is total work in. So, if we write W in, that is 1 minus M1 into H2 minus H1 plus H4 minus H3. So, these are very important because you will be getting, you can do, because if you apply steady state steady flow equation, right, to different devices, you will be getting the similar expression. For the sake of completeness, I have written over here, this expression will be very much useful while solving numerical problems. So, if you would like to summarize today's discussion, we have discussed about the ideal regenerative power cycle. Though we had discussed this in the previous class, today we have briefly touched upon that, and we have discussed the limitation of this. Perhaps the limitations, or I mean the limitations which are associated with this particular arrangement, are the motivation for this arrangement, that is open type feed water heater. So, using this particular arrangement, we had seen that this arrangement help us to increase the temperature of the feed water which would be supplied to the boiler, and this additional heat which is not supplied to the feed water by burning coal or burning fuel. Instead, that heat is taken from the steam which is flowing through the turbine. And I am telling you that this is very important. So, you can argue that okay fine, if we extract m1 kg of steam, then perhaps this, if we do not extract this steam will do further work and W out will increase. That is true. If we do not extract this amount of steam, so this steam will be doing additional work and W out will increase, but by extracting this amount of steam, we could increase the temperature of feed water. Not only that, since this amount of steam is extracted, the amount of heat that must be rejected also will decrease. So, the overall impact would be to raise the efficiency of the cycle, and that is what it is. So, extracting steam, momentarily you can find that we are going to compromise the W out, that is true, but this steam will increase the temperature of feed water before it enters into the boiler, which in turn will increase the efficiency by increasing the average temperature of heat addition. And had this steam been allowed to expand in the turbine, I do agree that we would have obtained more amount of work from the turbine, but at the same time the heat rejection amount would have increased. So, extracting, by perfectly designing this system and perfectly calculating the fraction of steam that should be extracted, if we can run, the overall impact would be the increase in efficiency of the cycle. And that it is very important. Till now we have shown only one feed water heater. It is possible to extract steam at different points from the turbine, and it is seen that if we can have 8 such arrangement, then efficiency of the regenerative power cycle would be exactly equal to the Carnot cycle. So, with this discussion I stop here today.